In this example, I'm going to discuss what happens with a converging lens, and let's start off with some of the numbers. There's going to be an object which is placed at a distance of 48 centimeters from the lens, and so I'll write object distance is 48 centimeters. This converging lens will have a focal length f equal to 12 centimeters. And let's imagine also that the object has a height of 1.8 meters. So this might be the height of a person. What I'd like to do is find out what is the image distance, what is the magnification, and what is the height of the image. And we'll do those computations in a moment, but first thing I want to do is complete a ray diagram so we can get a sense of what this would look like. So I've already set this up so that here we have a very thin lens, and I've located the two foci there on the picture. They're two units away from the lens, and so notice that the object distance 48 is 4 times as big as the focal length. So what I'll do is simply multiply that focal length by 4. And so I'll put the object distance here. Okay, so just so that I can draw everything to scale, the object distance is now 4 times the focal length. So that's the object, and I've drawn DO like this, right? That's that. Okay, now the rules for figuring out where the image is going to be, what we'll do is we'll take a ruler, and the first thing I'm going to do is draw a straight line that goes parallel to this optical axis. Remember that this here is the optical axis that cuts right through the center of the lens. I'm going to draw a line that goes parallel, and I'm going to draw it from the top of this object, okay? So there's a million different rays, a billion. There's an infinite number of rays we could draw, but we're going to draw 3 rays. The one that will go from the top of the object to the lens, what happens is once it hits the lens, the whole design of the lens is meant to deflect rays that come in parallel to the optical axis and have them go through the focus on the other side. Okay, so that's one light ray, and you can imagine it going in and out like that. Because that is the purpose of this lens, the converging lens, and the converging lens works the same way forwards and backwards, that means that if I send a light ray through the focus on the same side, it should have a similar sort of behavior. So if the ray goes through the focus on the same side, you just have to be a little careful with making sure that you have lined everything up as well as you can. These pictures are hardly ever perfect. But for a ray that goes through the focus on the same side, it hits the lens, and then it is made to go parallel to the axis. So it's kind of like the green lines that I just drew. It's kind of like that in reverse. So that's the other one I can draw. And right away I can tell roughly where I expect the image to be. It's where those things intersect on the other side. To be certain, I'll draw one final ray, and that's the ray that goes from the head of the object through the center of the lens. And the special thing about the rays that go through the center of a thin converging or diverging lens is that they don't get deflected at all. The whole design of the lens is to make those rays go straight on through. And I've drawn this well enough that they actually all intersect in the same place. And that's how I know where the image is going to be. So I'll put my blue dot there. That's where the image of just the head of the arrow will be. The tail, all the rays coming off of the tail would pass through the center along the optical axis anyway, and so those end up here. And so what that means is the head is down there, and the tail is along the axis. And so that is the image. I'll mark it with a letter I. And so now I can kind of already see what it looks like things are supposed to happen. I can see that the image distance should be something like what's illustrated in this picture. It's about 2.5 blocks, could be a little more, a little less, 2.5 blocks. 2.5 blocks, given that the focal length is 12 centimeters. If I multiply that by basically, if you do 2.5 divided by 2 is 1.25, right? 1.25 times 12. I might guess the image distance is going to be somewhere around 15 centimeters. I guess we'll find out. What else I can see is that the magnification, or maybe I'll talk about the height. The image height is definitely less than 0, right? Because we measure heights as going positive if it's above the axis. So heights are positive this way, and they are negative going this way. So the height is definitely less than 0. But also I can tell that the height is, or the magnitude of the height is definitely smaller. You can see it's a smaller image. And so what that means is that the magnification will not only be less than 0, but its magnitude will be less than 1. So I can write this, and I can write it's going to look something like this. So the overall magnitude will be somewhere between -1 and 0. And I would claim that that is going to be a real image. It really is the product, or it's the result of 3 real rays that are actually intersecting there. And so you could actually project that image onto a card or a screen or something like that. Okay, anyway, that's our expectation. So that's what we've just done, is we've used made a ray diagram, we made expectations here. And these are real rough based on our drawing. Now we can use the lens equation to actually figure out what things should be. So we have the lens equation, which is 1 over DO plus 1 over DI. That should be equal to 1 over the focal length. And we also have a relationship between, or the relationship that defines the magnification, which is either the image height over the object height. You can also set that equal to minus DI over DO. That is also the magnification. Okay, so let's go ahead and solve for the image distance using that first equation. Using the first equation, 1 over DI is equal to 1 over F minus 1 over DO. So we'd write that as 1 over 12 centimeters minus 1 over 48 centimeters. And then we're going to have to take the inverse when we're done with that. I could try to find a common denominator, which would make this 4 over 48 inverse centimeters minus 1 over 48 inverse centimeters. I guess that's 3 over 48. And I could actually do the math. That's the same as 1 over 16. So that tells me that DI is supposed to be 16 centimeters, reality. And so actually that's pretty damn close to what our expectation. Now, as far as the image height and magnification, let's go ahead and compute the magnification. That's maybe the easier thing to do at the beginning. I don't have the image height yet, but I do have the image distance. So I'm going to write this as minus DI over DO, which is minus 16 centimeters over the object distance, which we were told was 48 centimeters. And that is, you'll notice the centimeters cancel. That's equal to minus 1/3. So that is the magnification. And lastly, because we can set the magnification equal to the image height over the object height, we can solve for the image height, right? The magnification times the object height, that will give us the image height. In other words, it's minus 1/3 times the object height, which we were told is 1.8 meters. And so that is minus 0.6 meters. Again, it's negative, and that tells us that the thing is inverted, the image is inverted, and it's smaller in size, right? It's about 1/3. It's equal to exactly 1/3 of the size.